Hey Level 3s, Diploma kids, welcome back to 16.1. This is Part C. So what we're going to look at today or now is looking at actual data to see how we can work out the order of a certain reactant in an experiment. To do this, you'd actually have to do multiple experiments to make changes to A and then look at the outcome on the rate. In order to do this, you'd have to keep the other reactant or reactants constant. So if you look at all of your data, will always have the experiments will have one reactant keeping a constant concentration and then doing a change to one. So therefore you can actually look at the change on the rate. Now it's important to make sure that we understand here that this is just the initial rate of reaction, because we know rates change throughout an experiment and the initial rate has the biggest difference. So that's what we look at here. Okay, folks, let's launch into it. So if we look at this data, so we look at experiments where one reactant is kept constant. So in these experiment 1 and 2, that's Cl2. And we can see here that NO, the concentration, has been doubled. So what we need to do is look at what effect that has on your rate of the experiment. And you can see here that the rate has been quadrupled. So if we double the concentration and the rate gets quadrupled, that must mean that NO is second order. Okay, so now what we have to do is find the experiment where, or the experiments I should say, where NO is kept constant and we can observe the changes to Cl2. So this time we're comparing experiments 1 and 3 because they're constant, and we look at what happens. So if we look here, you can see that the concentration of Cl2 is halved. So when we look at the rate difference, okay, we can actually see that that's also been halved. Now, for some of you, you don't like scientific notation. Just turn it out of scientific notation, and it would be a lot easier for you to see. So that's probably a lot easier for a lot of you to see that number's been halved. So when the concentration was halved, the rate was halved, which means that's a proportional change, which means we're looking at Cl2 being first order. So therefore, if we write the expression, it's going to be rate equals K times NO in square brackets squared and Cl2. I hope that makes sense. It's explained in the next slide if you need a bit more clarification. Okay, so here's just a quick tidbit. It's really useful to make sure you've understood this. So this is just looking at, here's the type of order of reaction, and here is the situations that you could see happening. So if the concentration of A doubles, okay, and the rate doubles, then that means it is a first order. If A triples and the rate triples, then it's first order. So these are proportional changes. They do the same thing. So if A increases fourfold, then the rate increases fourfold. Okay, so it's all proportional. So now let's look at second order. You can see I'm ignoring first order because that's never any change, and so I think you've got that. So if A doubles and the rate quadruples, that means we're looking at second order. If A triples and the rate is times by 9, then that's going to be second order, and then times 4 is times 16, and that's second order. So these ones for second order can be a little bit harder to do if you're doing the multi-choice paper because you don't have the calculator, but they keep the numbers really simple. It's only in paper 2 that they'll give you niggly numbers, and all you have to do honestly is times your rates by either 2 or 4 or 3 or 9, and you'll come up with the answer straight away. So you get used to the right sort of numbers to plug in. Okay, another example, remembering that you cannot use the coefficients of your equation. You must look at the data in the experiment, and you must find one where the experiments where one thing is kept constant. So we're going to look at experiment 1 and 2 to start. Cl2 is constant, so we're looking at the order of OH minus. So when the concentration of OH minus is doubled, then the rate we need to look at, and you can see here it's quite easy to see that the rate has been doubled. So this is a proportional change. So we know if we're writing a rate expression that OH minus is to the power of 1, so we don't need to write anything. So let's have a look at rate order 2, the second thing, which is going to be ClO2. So we have to look at the change here. So we're going to compare experiment 1 and 3, and that's purely because we need to keep OH minus constant, and that 1 and 3 have that at constant. So what's the change in concentration of ClO2? And that change is that it's been tripled. And if we look at the rate here, I actually would have to put this into my calculator. My maths is pretty crap these days. You might be better at this. But what you can actually see is that this has actually been times by 9. So if this has been tripled and this has been times by 9, that makes ClO2 second order. So that should be written ClO2 second order, like so. And there's your rate expression. Okay, here's another example. Here you can see I've snapped all these off the internet, which is why they look a bit ugly, but you get the gist. So let's look at B first of all. A's being kept constant. When B is doubled, okay, the rate does nothing. So it's zero order. Okay, nothing, zero order, which means that B is having no effect on this reaction, this rate of reaction. So then if we look at A here, folks, we can see that, and we look at where B's being kept constant, so we're comparing 1 and 3, you can see that when A is tripled, okay, what happens to the rate here? The rate between this, and again, I wouldn't be able to do this without my calculator, but it's actually been timesed by 9, okay? So, therefore, this is going to be second order. Okay, hopefully that makes sense. It's just like before. So if we write this as a rate expression, we're not going to include B at all. So it's going to be rate equals K, and we only include the one that actually is affecting the rate, which is A to the power of 2. And we just leave off B altogether. Sometimes you'll see it like this, but we just don't need to worry about the B because it's not having an effect. Okay, so here's a task. I'd really like you to pause your video and give a go at this. And if you would like to, you can continue to listen to me. Otherwise, you can unpause when you're ready and check your answer. Okay, team. So we need to keep something constant. There's B constant. And so we look at A. A's been doubled. When A was doubled, the rate was doubled. So nice and easy. That's a proportional change. So A is going to be first order. So now we've got to look at B, so we've got to find one where A becomes constant. I've just chosen these two here, and we're going to look at what happens to B. So between 0.1 and 0.2, it's been timesed by 2. So what's the difference here that you can see? And the difference between these two here is that it's been timesed by 4. So instead of a proportional change, we've got to a power of 2. So therefore, B in this case is in fact second order. So if we write our expression, it's going to be rate equals the constant times A times B squared. Hope that makes sense. So there are 3 tasks here. You really need to complete these before moving on to the next section. So I'll go. You can read these now, answer it. Please pause here, answer this one, and here are the answers. They're all on the OneNote if you need them. Okay, final aspect, and I'm hoping I can finish it in this video. So mechanisms are what causes these rate of reactions, and mechanisms are steps that we think occur as the reaction happens. We can't observe them, we can't prove that they happen, they're just supported by kinetics, and so we believe this is what happens. So the best way of explaining that is looking at this example down below here, where the first step of the reaction is 2 NOs reacting to form N2O2, and then the second step is N2O2 reacting with oxygen to produce NO2. Now we don't ever see this N2O2 because it cancels out, you can see here. However, it's actually really important that this happen because this is what we call a 2-step reaction, and one of these steps will be slower than the other, and always the slowest step in a reaction takes over the entire rate of the reaction. It's like if you go tramping, you always go at the slowest tramper's pace so they don't get left behind, and rates of reaction is effectively the same. Now there's some terminology here, don't get too wound up by this, please. So unimolecular just means there's one reactant, bimolecular means there's two, and trimolecular means there's three. Although trimolecular is not very common, because to get 3 reactant particles to the correct activation energy is a hard task. So here's an energy profile. It's different to what you've seen before because this is a 2-step process where you've got one reaction's activation energy and another reaction's activation energy. Now we say the rate determining step in the reaction is the one with the greatest activation energy, which means it's the slowest step. Okay, so you can see here the activation energy here is far greater than it is here. So the rate determining step is this first hump. Okay, so step 1 is a much slower reaction than step 2 because the activation energy is way bigger. So we say the activation energy of the whole reaction is equal to the activation energy of that rate determining step. So the rate determining step determines everything. So when we actually add a catalyst, just for like future reference, the catalyst is actually added to lower the activation energy of that rate determining step. Okay, so rate expressions can actually be determined by mechanisms. Okay, so as the rate of reaction is determined by the rate determining step, the rate expression depends on the rate law for the rate determining step. So blah, 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 lots of words. Let's just have a look at what this actually means. So if you've got a rate determining step, so we'll get to how you work out what that is, and it's just one, there's just one thing going to products, then the rate law is it's proportional to that. Okay, so again, right now you don't know the rate determining step, but say you did and it was this 2A forms a product. Because there's 2, then that would actually be what we call bimolecular, and then it's a rate order 2. So if it was the rate determining step was A plus B, then the rate expression would be A times B, like so. Okay, so we can actually use the rate determining step and how it's formulated to formulate a rate law. So it's kind of like an extra way of being able to do this. So let's have a look at an example. Okay, so you're told in these ones what the rate determining step is. So here's the overall reaction, but here's it broken down into steps. And they're saying here that this first step is the rate determining step. Okay, so if that's the case here, then this is unimolecular, one thing forming these. And so that's what we use to create the rate expression. So we would write the rate expression simply K and the concentration of that. So I'll just go back to this. This was an example of this unimolecular where we would just write the rate law is to do with just that A. Hope that makes sense. Let's look at another example where it's not the first step that's doing it. It's actually the previous one, because this step here, if it's the first step, it's nice and easy because you would just look at, is it just this one reactant and then, or is it 2? And that's really easy. It gets a bit harder when we're looking at this one here where it's the second step, because you actually have to look at the substance before, because that's going to play an impact too. So let's have a look at this example here. So step 1, you've got NO and NO forming N2O2. And then the rate determining step is the N2O2 and the O2 forming 2NO2. Now, what you've got to keep in mind here is that if this is the rate determining step, then how was this made? And these two made this, so they have to be included somehow. So what we do is we look at this is what you would have if you were just writing from that equation, but we know that that's not correct because N2O2 is made from these two. So we actually kind of forget about this and look at where this came from. And this would be a bimolecular, so NO times NO, so making second order, and then also times by O2. So the actual rate expression for this one here is rate equals K NO second order times O2. So you actually ignore that part, even though it was the rate determining step, because the only way to have made this was from these. So here's a wee summary. This is the end of this section. You need to practice, practice, practice. give it a go, and we're going to spend the whole next lesson going through this stuff as well, in particular these last mechanism things. Okay, team, well done. Please complete these questions for homework.